So we got our invited speaker, Elin Winkler, next. So Elin got her PhD in physics from Balseiro Institute at the Cuyo National University. She has been a researcher at the National Council for Scientific and Technical Research and also at the National Atomic Energy Commission. And she's also a professor at Balseiro Institute at the Cuyo National University. And today she will be talking about the design of core-shell nanoparticles for optimizing the magnetic hyperthermia and the catalytic activity. So this is, we're right on time. I guess, Elin, you can go ahead and take over.
Okay, thank you, Jason. Thank you for the invitation and the presentation. As you say, today I'm going to talk about how we can design and fabricate nanoparticles in order to optimize the magnetic hyperthermia and the catalytic activity. Well, I work at the Institute of Nanoscience and Nanotechnology that is located at the south of Argentina in a beautiful city named Bariloche. Well, as an introduction, I mentioned that the magnetic nanoparticles are used in many applications, and in particular, one of the parameters that determine the range of application of the nanoparticle is the magnetic anisotropy. In example, for hard magnetic material, the system is useful for the design of magnet and also for the magnetic storage devices. Instead, for biomedical application or environmental remediation, is used, one of the property requires is low magnetic anisotropy. And in this talk, we're going to see how we can tune the magnetic anisotropy. Well, when we talk about nanoparticle, we mean material whose size is smaller than 100 nanometers. And in particular, for magnetic nanoparticles, below the transition temperature, the pre-temperature or the new temperature, the material organized forming multi-domain structure. However, when we reduce the size of the material, in particular for ferrite, the size should be smaller than 40 nanometers, more or less, depending on the material. The formation of the domain wall, it has a cost of energy, so the material do not save any more energy forming a domain wall, so the nanoparticle behave as a single domain nanoparticle. So this system presents an internal order which is determined by the exchange interaction and present a large magnetic moment, and this magnetic moment is aligned along one direction determined by the magnetic anisotropy. The magnetic anisotropy, as you know, is proportional to the anisotropy constant that depends on the magnetocrystalline anisotropy or the stress or also the shape of the nanoparticles, and also is proportional to the volume of the nanoparticle. So if we reduce the size of the nanoparticle, this anisotropy energy will be reduced and we will reach the situation where the thermal energy will be larger than the anisotropy. So in that case, the energy that determines that the magnetic moment is along one direction is smaller than the thermal energy, so the magnetic moment will start to fluctuate. When we arrive to this situation, we say that we are in the superparamagnetic regime. One of the characteristics of this regime is that the systems do not present any remanence, do not have remanence magnetization or coercivity. And this is one of the requirements for the biomedical application because we want to avoid the agglomerations. So when we inject the nanoparticles in a biological system. So we require magnetic nanoparticles, superparamagnetic at room conditions. But what happens now when we apply an AC magnetic field? In that case, we will observe, depending on the frequency of the magnetic fields, we will observe a phase shift between the magnetic moment and the magnetic field. So the system will present losses, magnetic losses. That magnetic losses we can measure as a coercivity cycle, and in each cycle of the AC magnetic field, the material do lose magnetic energy and dissipate that energy to the environment, and the system rise the temperature. So this is the concept used in the magnetic hyperthermia therapy. The nanoparticle system absorb magnetic energy and dissipate that energy as heat to the medium. In that way, the temperature of the medium rise, and we are looking that the temperature rise in 42, 45 degrees. In that case, when we rise the temperature of the medium, it's induced a cell death, induced apoptosis of the cells in the system. So this therapy, for example, is approved for very few cases. One of that is the glioblastoma, this brain cancer, where the therapy is the therapy consists in you inject the nanoparticle system into the tumor, and then you apply a magnetic field, and in that, like that, the temperature of the local, the zone where the tumor is located, rise and produce a cell death. So the advantages of this therapy is a local therapy. It has a very small area of action, allows the remote application, and also is a chemosensitizer. However, it has some limitation, and for that reason, it's only approved for a very few cases. There are several limitations, but we're talking about here that these two in particular, that one of the limitations is the low heating efficiency, and also that the heating efficiency depends on the viscosity of the medium. For example, when you make an experiment in different medium, in water or inside the cell, you obtain different, the medium heat reach different temperatures. Also, there are another issues as the toxicity, of course, of the nanoparticles or the agglomeration. But in this talk, we are going to see how we can improve these particular 2 points. So, to optimize the hyperthermia, we have to understand the mechanism behind the relaxation of the magnetic moment. And there are 2 main relaxation mechanisms. One of that is the Brown relaxation, where when you apply a magnetic field, an AC magnetic field, the magnetic moment relaxes toward the direction of the magnetic field, making a mechanical movement on all the nanoparticles, not only the magnetic moment, if not rotate all the nanoparticles together with the magnetic moment. In that case, this relaxation mechanism will depend on the viscosity of the medium. The other mechanism is the near relaxation. In that case, only the magnetic moment inverts its orientation when you apply an AC magnetic field, and in that case, as only the magnetic moment rotates with the magnetic field, depend only on the magnetic parameter, the anisotropy energy, which means the anisotropy constant and the volume. Besides, as in many phenomena in the physics, the system will relax toward the mechanism with smaller relaxation time, which means, for example, for system with small anisotropy, this relaxation mechanism will be smaller, so the system will relax toward relaxation. On the contrary, if the viscosity in example is smaller, the system will relax toward Brown relaxation. So, if we can't change or control the magnetic anisotropy of the system, we have a tool to select one mechanism or the other. And here you can see that we can change the volume of the nanoparticle, but in that case, we're changing the nil relaxation and also the Brown relaxation. So the correct tool to modify is the anisotropy energy. And we can do that by the design and fabrication of core shell magnetic nanoparticles. For example, if we combine in a single nanoparticle 2 different phases, a soft ferromagnetic material and a hard ferromagnetic material, At the interface, there is an exchange interaction, and in that way, both phases are coupled, and we will invert both phases together when we apply the magnetic field. In that situation, which is a rigid coupled situation, the anisotropy energy will be an average of the magnetic parameter of both components and also the coercivity field. And if we systematically change in examples the stoichiometry of the shell, we are able to systematically reduce the needle relaxation, and in that way, when the needle relaxation is larger, the system will relax toward the brown relaxation, on the contrary, will relax toward the needle relaxation. A point that I want also call the attention is for biomedical application. We look for a system where the near relaxation is the dominant mechanism, because the nanoparticles are usually fixed inside the cells. So how we did that? Well, we select a magnetite to fabricate the core, and we encapsulate that with cobalt zinc ferrite. And we change systematically the stoichiometry. Why we did that? Because the cobalt ferrite is a hard magnetic material, the anisotropy is 10 to 6 erg over cubic centimeter. Instead, in the other extreme, the zinc ferrite, the anisotropy is 2 orders of magnitude smaller. So we fabricate the samples. First, we fabricate the magnetite. Here you observe the core of the nanoparticle, whose size is 7.5 nanometer of diameters. Then we split that batches in 5 batches, and we overgrow the shell. These are a representative TEM image where the core shell, the size of the core shell nanoparticles is 10 nanometers. And in this TEM image, for example, you can observe different ways that we can characterize the core shell structure. This is dark field, where the bright component corresponds to the phases with a particular crystalline direction. In this high resolution TEM image, you can observe different crystalline orientations. And also in this image, for example, where the image is reconstructed from a particular diffraction point, you can only obtain information of that particular crystalline plane. So we observe, for example, that both phases are oriented along the same direction, but because of the mismatch between the core and the shell, you observe some disorder at the interfaces. Here are all our samples. This is the core, and these correspond to the samples with different stoichiometry of the shell. This is the cobalt ferrite with 25% of zinc, 50% of zinc, 75, and zinc iron ferrite. Related to the magnetic properties, well, this measurement corresponds to the zero field cool and field cool magnetization curve, where we can observe a change from superparamagnetic to blockade regime. And this kind of measure allow us to calculate the distribution of blocking temperature. And from the maximum of the distribution, we can obtain the magnetic anisotropy of the system. So this measurement corresponds to the sample with the shell without zinc, the cobalt zinc ferrite. And then when we replace cobalt by zinc, we see how the anisotropy is reduced. In fact, in this way, by systematically changing the stoichiometry, we can change the magnetic anisotropy 1 order of magnitude without modifying the volume of the nanoparticle, because by this way, all the nanoparticle system has an average of 10 nanometers of diameters. Similar result we measure we obtain from the hysteresis cycle, where we observe a systematic decrease of the coercivity field as a consequence of because the magnetic anisotropy is reduced when we change the cobalt by the zinc. So we arrive to the magnetic hyperthermia experiment. To perform this experiment, we disperse 0.5% of nanoparticles, in this case in hexane, which is a liquid that has very low viscosity, and we measure with different frequency. The amplitude of the AC field is 200, and we measure with different frequency. What we measure? Well, we measure how the temperature is rise as a function of the time. And for example, in this measurement, the measurement corresponds to the larger frequency, we observe that the system increased 15 degrees in less than 1 minute. Yes, we start from room temperature in these cases. And for all the frequency, we observe similar behavior. So we are going to focus only on one. We measure 5 samples, and we observe 2 different behaviors. When the shell of the sample has a lot of zinc, is zinc-rich shell, which remember is the sample with very low anisotropy, the system do not produce any or very low hyperthermia. However, the sample that has a lot of cobalt in the shell, remember, is the sample with very large anisotropy, we observe that the system induces hyperthermia. So our hypothesis, or what we think, is because the system has very large anisotropy, the near relaxation is inhibited and should relax toward the Brown relaxation. On the contrary, here, the relaxation mechanism will be the near relaxation. And to quantify this measurement and to prove that, or to check that that is what is happening, we calculate the specific power absorption that accounts the power absorption of the system. And this parameter is proportional to the change of the temperature with the time and the specific heat of the material. So here we are drawing as a function of the zinc concentration. Again, samples with low zinc concentration, or which is better to think, large cobalt, which is very large anisotropy, produce a pretty larger power absorption, and suddenly we will change a little cobalt by zinc, cobalt by zinc, yes, the specific power absorption drop. So here there are a change of mechanism from Brown to nil. How can we prove that? Well, we took the same nanoparticles and we dispersed that in a medium with very large viscosity, like the butter oil. In that case, we see the viscosity 3 orders of magnitude larger. When we disperse the nanoparticles in this medium, we are avoiding the movement of the nanoparticles, so the Brown relaxation is inhibited. And in that case, well, we observe that as the nanoparticle cannot move, the nanoparticles do not produce any hyperthermia. So up to here, we see that with this strategy, by changing the composition of the shell, we can change the relaxation mechanism. Well, but now we want to optimize the near relaxation for the biomedical application. So we have to see how we can produce a heating here with this mechanism. And to do that, we go and see the Rosenweight model. This is a very simple model, but help us to predict which should be the condition for the optimal specific power absorption. And this model says that the optimal condition corresponds when the characteristic time, relaxation time of the system, could be nil, Brown, or a mix of both, is, well, in fact, in this model say that is the system relaxed toward the Brown relaxation of nil, but this relaxation of the nanoparticles should be equal to the frequency, it should be equal to the characteristic time, this is 1 over, so 1 over the characteristic time of the AC field. One way to look for that case is making this kind of drawing. We calculate for all the samples the relation of the nil and Brown relaxation time because we have all the parameters, and this corresponds, for example, to our samples when they are dispersed in the sun. The 3 relax toward the brown because the brown is smaller than the nil. Then we disperse the samples in butter oil and shift toward the left in our graph. And this red line is when the nil is equal to the characteristic time of the AC field, which correspond to the optimum situation. In fact, we can see that these 3 samples that correspond to these 3 when they are dispersed in exam are, in fact, in the situation of the optimal heating. So if we want to our system relax toward the middle relaxation, we should fabricate nanoparticles around this situation. So remember, this is the cobalt ferrite, when the shell is the cobalt ferrite, this is the zinc ferrite, and so we have to adjust the composition. So we made that, we start to fabricate, we fabricate another batch, the magnetite, and then we overgrow the shell, and systematically we find the maximum, and in that way, so we can optimize the specific power absorption where the near relaxation is the relaxation mechanism. Well, part of the results were published in Nanoscale and illustrate the back cover, and we asked for a drawing to an artist, an Argentina artist, Pablo Bernasconi, that made this beautiful drawing that is a world of a nanoparticle made by part of watches. And for us means all the engineering that you have to do to optimize the relaxation time. So all the problems are not solved because from material science we can design the nanoparticle, we can design the volume, tune the relaxation, optimize the SPR. We can increase the temperature over 50 degrees or to produce the thermal ablation, or we can go between 40 and 42 degrees to produce cell apoptosis. However, there are still many things to solve. For example, one of the problems is that if we increase the temperature too much, produce a damage in the health tissues and also produce inflammation. And also it's observed that the temperature is not so large. The system shows, the tumor shows recurrence, and the new cells shows heat tolerance. So all the people working in the area is looking for how we can optimize the effect of the magnetic hyperthermia, so it's not necessary to rise the temperature so much and even produce a cell death. One way to do that is a new research line that it's called chemotherapy, chemodynamics, is remember that the nanoparticle the iron has activity, catalytic activity. For example, in presence of peroxide, decompose the peroxide and form these molecules that are free radical, are very reactive molecules. In fact, by this way, is used this catalytic activity is used in environmental remediation because induce oxidation of organic molecules and produce a degradation of organic contaminants by this reaction. The iron 2+, the iron 3+, decompose the peroxide and form this free radical, which is called reactive oxygen species. Well, these reactive oxygen species are also produced inside the cells. This is a same image of the cells where the nanoparticles are internalized, for example, here in the lysosome and another part of the cells. And as a consequence of the metabolism of the shell, it produces ROS, but the cells has their own mechanism to balance the concentration of these reactive species. However, when in some situation, when there is some imbalance and produce more than more reactive oxygen species than the amount that the cells can balance, these ROS are highly toxic and produce oxidative damage of the cellular membrane, which is called lipid peroxidation, produce oxidative stress and cell death. So this is the mechanism that we are looking for to potentiate the hyperthermia. As the free radicals are catalyzed in the surface of the nanoparticle, we can produce more free radicals. So we wonder which is the role of the iron, of the metal iron, in the production of reactive oxygen species. And to answer that, we fabricate several new nanoparticles of more or less 10 nanometers, magnetite, where the ions, remember this is a surface problem, so it's the only matter is the stoichiometry of the oxidation state of the metal ions at the surface. The magnetite has iron 2 plus and 3 plus. We oxidize this same system where all the nanoparticles, all the iron of the nanoparticles are 3 plus. Then we replace iron 2 plus by nickel, nickel ferrite, and we replace the iron 2 plus by manganese. How we measure the ROS production by electron paramagnetic resonance that allow to quantify and identify the free radicals. Remember that the free radicals are very reactive molecule. It has very short lifetime, so we have to use spin trapping. Spin trapping is a diamagnetic molecule that traps the free radical and produce a more stable free radical that can be measured and related, depending on which radical the spin trap, the signal is very different. For example, this EPR signal corresponds to the spin trap that traps the hydroxyl group. In that case, is the methyl group, and this signal corresponds to the superperoxide. This is one of the measurements of the nanoparticle. Is the nanoparticle dispersed in a liquid, in water solution containing peroxide and the spin trapping, and we can make a deconvolution of this signal by making a fit of the signal. We can identify and also quantify, because the area of this signal is proportional to the concentration. And also we use the manganese as the pattern samples. Well, in that way, we can quantify the concentration of free radicals, and this, for example, corresponds to the magnetite, that is the sample that produces larger concentration of radicals, and when the surface is oxidized, or in the case of manganese ferrite or nickel ferrite, the concentration of free radical is reduced. Well, this measurement is performed at 4.8 pH, and when the measurement is made in a neutral pH, the system do not produce free radicals. So when we call, sorry, we are near to the end of the talk. Well, we also measure, we also made in vitro experiments. In this case, the nanoparticles are internalized in BB2 cells, and we quantify by a fluorescence marker. These two measurements correspond to the control, and this is the fluorescence produced by when the nanoparticles are internalized in the cells. The measurements were measured at 37 degrees, that produce more radicals than the control, and when the measurement is made and hyperthermia condition, produce even more free radicals. So, by this way, I was a very short summary, but this kind of measurement, this kind of design of nanoparticle also make us a tool to select if we want to make nanoparticle with active surface that produce radical and can potentiate the hyperthermia therapy for cancer therapy. And also, if we want to use this nanoparticle, for example, for MRI or ophthalmological treatment that you need inert nanoparticle, you have to oxidize the surface. So in that case, do not produce toxic free radical. And here I arrived to the conclusions. I just want to say that the core shell architecture, or by the design of the material, you can be able to tune the properties of nanoparticle to optimize the magnetic hyperthermia and also the catalytic activity for cancer therapy. And to finish, I remember this aphorism of Hippocrates that I think this the magnetic hyperthermia and the chemiodynamic is a modern view that what it said Hippocrates in the Greek, in the ancient Greeks, that he said that the disease which medicine do not cure, iron cures; those which iron cannot cure, fires can cure. And in this case, well, the magnetic hyperthermia is a modern way of fire, and the nanocatalyzers, the iron used as catalytic activity is the role of the iron. Well, this is the people working in nanoparticle in Bariloche, and our collaborated in Spain and Italy and the agency. Well, thank you very much.
Thanks a lot, Elin. It's a very great talk. I think we have a little bit of time for questions.
Yes, I don't know how I'm with time.
If you can, okay, so we got Ron over here.
Hi, Elin. Thank you for the very nice talk. Could we refer to your slide? I think it is number, maybe number 10.
I don't know.
And it's the one with the core shell magnetization curves, both versus temperature and versus
Maybe this
yield.
one?
And no, yes, this
The
one.
hyperthermia.
Go back one. That, yes, this one.
This one?
This one. So on this, can you say what is the measuring field for the magnetization as a function of temperature? Because it's
Yes,
clearly quite low.
Yes. Yes, in this kind of measurement, we use very low magnetic field. In this measurement, I didn't write here, but we used to use 50 worsteds, no more than that. If not the 50.
About 15?
50 or maybe
50, 50.
50.
Yes. So you can,
50.
if you look at the hysteresis loop on the right there, those low fields are much lower than the saturation, of course. I wonder if that affects your determination of the anisotropy constants. For example, if you start at the top with x equals 0, there's a very nice progression from x equals to 0 to x equals 0.5. In terms of the magnetization levels. And this is because for those compositions, the hysteresis loop is quite pronounced. There's a lot of hysteresis. So you're much below the saturation level. Whereas x equals 0.75 and x equals 1, where now you have no cobalt in the shell, your hysteresis loop is very narrow. So the character of these magnetization curves changes. You can look at the field cooled value, for example, at the lowest temperatures, it increases quite a bit. So really the question is, does that affect your determination of the anisotropy constants?
Yes. Well, for this kind of measurement, of course, you should use the low the magnetic field that you apply should be much lower as you can. If we reduce more, we won't observe any signal. So we used to measure with 5 or worsteds. If we increase the temperature, what would happen is the blockage temperature will shift, and as you say, the measurement of the anisotropy constant will be more far than the real one. With this magnetic field, the 50 worsted, because we also can, the other measurement that it can be done is the remanence measurement. In that case, you measuring the remanence, you call the system applying magnetic field, you turn off the field, and then you make the measurement. It's another way to determine the blockage temperature and the anisotropy. And for that field, it's more or less the same. We do not observe many differences. Sometimes, if the system has a low magnetization, unfortunately, the measurement should be done with larger magnetic field at 100 worsted, for example. But in this case, I think it's pretty, the data within consider with all that consideration, it's right. And the magnetic cycle is, in this case, is measured at low temperature. And well, I think I didn't say during the talk, for the experiment, it's important that at room temperature is superparamagnetic. So in all these samples are still superparamagnetic at room temperature. Although the cobalt ferrite is very anisotropic material. So I don't know if that answer your question.
Yes, thank you very much, Elin. Very nice talk, and I liked your quotation of Hippocrates at the very end.
Yes.
Thank you.
It's different.
One more question, if you can answer fast from the chat. I read, how do you determine the quantitative amounts of cobalt or manganese or zinc in the shells, by the starting materials or by some other method? Yes. By Sarah.
Yes, we didn't measure, I didn't show here, but by XPS spectroscopy, we quantified all the ions in the publication, are shown on that measurement. Yes, we quantified. In fact, this I mentioned here is the nominal. This is important because all the talk I refer to the nominal concentration, but the real amount is lower. In fact, we never reach the zinc ferrite because it's important. When the zinc ferrite is an antiferromagnetic material. In this case, we never reach that nominal concentration. So it's ferromagnetic. And the amount of the metal ions, yes, that quantification is in the publication, right? Yes.
Yeah, we thank you once more. Whoever wants to continue this interaction and discussion with Elin can move to GatherTown. I just pasted the link on the chat.